Today, let's develop a little further some of the basic notions of point set topology, which we started in the previous video. Take a point A in Rn. An open neighborhood of A is simply an open set containing A. This is a convenient way of referring to points that, in some very loose sense, we consider being close to A. So an open set is a neighborhood of each of its points. At this moment, it sounds probably like the word neighborhood is synonymous with set. That's not quite right, because the empty set is not a neighborhood of anything. If A is any point, then an open neighborhood of A would have to contain A, so it's automatically a non-empty set. In fact, U would have to contain more than just A. By definition of open, U would have to contain some open ball centered at A, with positive radius. So already it has an uncountable number of points. At least in Rn, this is true for n at least 1. In fact, the simplest kind of open neighborhood we can describe is an open ball centered at A. Sometimes we just talk about a neighborhood of A. That's any set containing an open neighborhood of A. In my picture, n isn't an open set, but it does contain an open ball centered at A, so it's a neighborhood of A. And sometimes we talk about a deleted neighborhood of A. This is just a neighborhood of A with the point A removed. You have seen deleted neighborhoods before. The definition of a limit in calculus uses deleted neighborhoods. When you take a limit as x approaches A, you only consider x close to A but not equal to A. So x is in a deleted neighborhood of A. Let A be any set of points. Now we consider another point x, which may or may not be in A. We say that x is a limit point of A if every deleted neighborhood of x contains some point of A. This means there are lots of points of A close to x other than x itself. Another way to say the same thing is that there is a sequence of points in A other than x itself, converging to x. A limit point is also known as a cluster point or an accumulation point. The idea is that inside the set A, you can find points which cluster around x, which is to say they accumulate around x. It's very easy for a set A to have lots of limit points. Note that a limit point is not the same thing as a limit of a sequence or a limit of a function. That's why many people prefer the terminology of cluster point or accumulation point. In this picture, A is a region which doesn't include its boundary, and in this example, the cluster points are all the interior points of A plus all the boundary points of A. But it's also easy for a set A to have no limit points. We'll see examples of that shortly. And by the way, boundary points are not the same as limit points in general. There is another concept of a boundary point in topology, but this introduction is too brief to go there, so you can easily look up that if you want to find out. The derived set of A is the set of all limit points of A. It's denoted A prime, just like the prime symbol from calculus where we talk about f prime, the derived function. Although I wouldn't suggest that you try looking very far for a connection to derivation in calculus. Here are some examples. You should check that the set of integers has no limit points. Every real number is a limit point of rationals. This is just saying that every real number is a limit of a sequence of distinct rationals. For every interval, the limit points are points of the original interval together with any missing endpoints. The set of rational numbers 1, a half, a third, a quarter, a fifth, etc. has exactly one limit point, that's 0. A finite set of points cannot have any limit points. Now, let A be any set of points in Rn. Let's go over how you test whether or not the set A is open. Also, whether or not the set A is closed. On the one hand, A is open if and only if it's a union of some collection of open balls. This is equivalent to saying that every point of A is the center of some open ball contained in A. In place of open balls, any open neighborhoods will do here just as well. It's easy to prove that these two conditions are equivalent. I would probably take the first statement as the definition of open, and the second condition becomes a more natural way of testing to see if the set A is open. But it really doesn't matter which one you take as the definition, since we can easily prove they are equivalent. If you haven't thought about this, you should stop the video and convince yourself why these are saying the same thing. Now the question is, what can we say for closed sets that is comparable to this? I would usually define a set as closed if and only if its complement is open. But then it's nice to have another way to test for a set to be closed, otherwise taking complements and checking for the complement to have open ball neighborhoods at every point, it just gets a little too roundabout to be readable. So here is an equivalent condition. A set is closed if and only if it contains all its limit points. If you want to actually test for a set to be closed, this seems to be the more natural criterion to use. Before we use this criterion, we should actually prove that these two conditions are equivalent. It's not hard. Here's the statement as a theorem. We'll prove this first in the forward direction. Suppose A is closed. So if I denote the complement by U, then U is open. I'm trying to prove that A contains all its limit points. If not, then there is a limit point X that lies in the complement U. In this case, since X is a limit point of A, the deleted neighborhood, U take away X, must contain a point of A. That's not possible, since U is the complement of A. So, U cannot contain any limit points of A. In other words, all limit points of A must actually lie in A. This completes the proof in the forward direction. For the converse, suppose A contains all its limit points. Again, we'll denote the complement of A by U. In order to show that A is closed, we must show that U is open. So let X be a point of U. Since X is in the complement of A, it certainly cannot be a limit point of A, right? All the limit points lie inside A. So X has an open neighborhood V, which doesn't contain any point of A. Why is this? Well, the deleted open neighborhood V take away X has no point of A, but also X itself is not in A. That means V is an open neighborhood of X contained in U. And this proves that U is open. So its complement A is closed. That's our proof. Everybody wants to talk about closure. How do you find closure? So let's talk about how you do that. Let A be any set of points. Then there is a unique smallest closed set containing A, called the closure of A, denoted A bar. If A is already closed, then the closure of A is A itself. Well, how do you find the closure of A? The theorem says that if you take the intersection of all the closed sets containing A, that should be the closure, A bar. But that description of A bar is not very explicit. A more explicit description of the closure is motivated by the previous result. Start with the original set A. Then, in order to get closure, you'll have to also throw in the limit points of A. But now the question is, do you also need to throw in the limit points of the limit points? And then the limit points of the limit points of the limit points, and so on, in order to get closure? Or if you just take A union the limit points of A, does that already give us closure? Does it give us a closed set? This theorem says yes, we can stop with A union the derived set of A. And that's already a closed set, so it's the closure of A. So let's get to work proving this. Let's denote by script K the collection of all closed sets containing A. The theorem says we only need to intersect all the closed sets in this collection to get A bar. It's useful to observe that there is at least one set in this collection, script K. That's because Rn is a closed set containing A. So Rn is a member of this collection. Now we define A bar to be the intersection of all the sets in our collection script K. Here are a couple ways to write that. There's a short way and a slightly longer way. This is the intersection of all closed sets containing A. Of course, A bar is a closed set since it's an intersection of closed sets. Also, A bar contains A since it's an intersection of sets containing A. Well, if A bar is a closed set containing A, then A bar is a member of our collection, script K. So, if A bar is one of the sets we're intersecting to get A bar, evidently from what we just said, every member of our collection, script K, has A bar as a subset. This just says that A bar is the unique smallest member of the family script K. Now all that's left is to prove the formula in the last line of the theorem. Since A bar is a closed set containing A, by the previous result, it also needs to include all the limit points of A. So to prove that this is equality, all we have to do is to show that A union A prime is already closed. In other words, this set already contains all its limit points. So just to repeat our plan from the previous slide, what's left to prove the theorem? We just need to show that the set A union A prime is closed. And to do that, we show that this set contains all its limit points. So, let X be a limit point of A union A prime. We only need to show that X is in A union A prime. So, take an open neighborhood U of X. If every deleted neighborhood U take away X has a point of A, then by definition X is a limit point of A, so then X would be in A union A prime. In that case, we'd be done. Well, if that doesn't hold, then there is some deleted open neighborhood U take away X containing no point of A. But of course, this open neighborhood has to contain a point of A union A prime, since X is a limit point of A union A prime. So then, U take away X would have to contain no point of A, but it must contain a point Y in A prime. Now, U take away Y is a deleted neighborhood of Y, which is a limit point of A. So, U take away Y contains some point of A. But what can this point be? Has to be a point in U take away Y, but it can't be in U take away X. Aha! This point has to be X. So, we must have X in A. You see, we had two possible cases. In the first case, x was in A prime. In the second case, x was in A. Either way, x must be in A union A prime. That is how we prove that A union A prime is closed. And I'll remind you that's the last thing we had to do to prove the theorem. Some examples. The set of integers has no limit points. So the closure of the set of integers is just itself. The closure of the set of rationals is the set of reals, since the derived set is already the entire set of reals. The closure of any interval is again found by taking the interval together with any missing endpoints. The empty set and the real line are already closed. So for each of these sets, the closure is the set itself. For the set of fractions 1 over n, where n varies over the positive integers, remember the only limit point is 0, so we pick up that one extra point to get the closure. A finite set of points has no limit points, so the set is closed. So its closure is itself.